So hi again, this is Mark Breederland again with Michigan Sea Grant. I'm based here in Traverse City, Michigan. Welcome to our first webinar of 2019, which is hosted by the Great Lakes Sea Grant Crude Oil Transport Network. I serve as the Michigan Sea Grant representative on this team, and it's a pretty broad geography. If you know the Great Lakes system, our Sea Grant system is from Minnesota to actually New York and Vermont. And I have a colleague there at Lake Champlain that's even a part of our team. So again, this is our first webinar of 2019 hosted by our team. This crude oil transport webinar series is meant to provide the latest research and resources to stakeholders in the region to help inform decision-making around this complicated and complex issue. Anyone with a vested interest in how crude oil and associated products move through the region will find some of the content informative. Let me give you a few logistics before we get started here to give maximum time to our presenter today. So first of all, the webinar is being recorded and is going to be available on our crude oil transport website. You can see the name there. That's GLSL for Great Lakes St. Lawrence crudeoiltransport.org. You will be invited to submit questions through the Zoom questions and answer box. I think you'll find that on the right of your screen. So at the end of there will be a Q&A session at the end of the talk, but we will be ending right at 3 o'clock Eastern time. And I know our presenter has to get back on the road. One more note and kind of a plug here. Our second webinar in this series is July 23rd. The same time with Stephen Keck, who's the Chief of Contingency Planning and Force Readiness for the U.S. Coast Guard out of the sector Sault Ste. Marie. So I hope you can look at your calendars and you'll find the information on their website and join us as well for that interesting webinar. I think those are all my logistics. We have a wonderful team at our Ann Arbor Sea Grant office that's helping out, and they'll introduce themselves a little bit later in the talk. But I think with all those, that's the logistics that we needed to cover. And it's now my pleasure to introduce Dr. Guy Meadows. Guy Meadows serves as the Robbins Professor of Sustainable Marine Engineering and was the first director of Michigan Technological University's Great Lakes Research Center, Michigan Tech as we call it here. So Guy was also a faculty member for 35 years at the University of Michigan's College of Engineering in Ann Arbor, where he directed the Marine Hydrodynamics Lab and the NOAA Cooperative Institute for Limnology and Ecosystem Research, among many other things. Notably for today's webinar, he served on the Michigan Governor's Pipeline Safety Advisory Board from its founding in 2015 until his resignation in 2017 to take on this Herculean task of coordinating a multidisciplinary team of academics and scientists to actually complete a risk analysis and estimate potential total liability for a worst-case oil spill scenario at the Straits of Mackinac. We're really excited to have Guy here to tell us today. He's here. The title of his presentation is Great Lakes Big Team Science and the Independent Risk Analysis for the Straits of Mackinac. Thanks so much, Guy. We're going to turn it over to you.
Thank you, Mark. I appreciate that introduction here. Let me share my screen. Thanks, everyone. Have a good afternoon. I'm Guy Meadows from Michigan Tech, and I'd like to share with you a little bit of the history of how we got involved in the independent risk analysis. First of all, Michigan Tech has two locations in Michigan. The main campus is on the Keweenaw Peninsula in central Lake Superior, and as you can see from this satellite image, far above the snow line. We're about 7,200 students, 481 faculty, divided over 7 colleges and schools within the main university. We have a satellite office in Ann Arbor, Michigan Tech Research Institute, which does primarily very high-level advanced remote sensing, and that's about a 60 to 70 person operation in Ann Arbor. To refresh, what we're going to be talking about today is Line 5, which traverses the Upper Peninsula, crosses the Straits of Mackinac, and proceeds on down to southeastern Michigan and crosses the St. Clair River at Port Huron and Sarnia. Very contentious issue, and I'd like to give you a little bit of history on how we became involved and how ultimately we were asked to organize Michigan's universities to conduct the risk analysis. The history in the Straits is we began developing advanced underwater sensing techniques with autonomous underwater vehicles in order to monitor the Enbridge pipeline and their crossing through the Straits. That developed into real-time monitoring for the Straits. We added one of our environmental monitoring buoys, publicly accessible buoy that reports every 10 minutes a whole variety of meteorological and oceanographic parameters, and perhaps most importantly, wave heights in the Straits and the vertical distribution of currents at 1 meter intervals from the surface to the bottom. Concurrent with that, with the creation of the Great Lakes Research Center here in 2012, the university added at its own expense a supercomputing cluster and essentially 6 new faculty hires devoted to water research. The university takes the health of the Great Lakes very seriously. One of those hires was in advanced numerical hydrodynamic modeling. Professor Peng-Fei Yu is actually one of the creators of the current most advanced modeling system, FVCOM, Finite Volume Coastal Ocean Model. He was one of the developers when with his time at University of Massachusetts. Those activities proceeded to the point that when the previous governor of Michigan created the Pipeline Safety Advisory Board, I was asked to represent Michigan's 13 public universities and have a seat on the board. I'd like to tell you a little bit about each of those 3 activities, however, that led up to my appointment on the Pipeline Safety Advisory Board. The autonomous underwater vehicle that we operate in the Straits of Mackinac is, as its name implies, fully autonomous. We pre-program it, can send it away for up to 8 hours at a time. Its primary sensor on each side of the vehicle is this very high resolution interferometric sonar system, the EdgeTech 2205. You can see the very bottom of the vehicle is also equipped with a camera and a strobe light. But the main point I'd like to make is that these lenses on both sides are depressed from the surface and do not fully cover underneath of the vehicle. And you'll see that when I show you some examples. But the vehicle is fully autonomous. We decide on a pre-programmed course. We ask it to fly about 2 meters above the bottom to follow the terrain of the Straits. And at the place where the Enbridge pipelines cross the Straits, the maximum water depth is about 240 feet. And we ask it to fly approximately 18 meters offset from the pipeline to place the pipeline in the very sweet spot of the sonar images. In the next slide, I'll show you that. So the vehicle is now lining up on its line. You can see it's beginning its dive. Once it leaves the surface, we have absolutely no control over the vehicle. We cannot talk to it. We cannot send it other commands. It travels at about 2.5 knots. This is an example of the imagery, very high resolution side scan sonar imagery that it produces. The black stripe down the center is that blind spot directly under the vehicle. The Enbridge pipeline is on the left side of the diagram here, traversing vertically from top to bottom. The pipeline is 20 inches in diameter, and you can see the terrain being very nicely articulated by the sound image here. This is a pile of dirt that was placed over top of the pipeline when it was originally placed on the bottom. You can see the excavation marks here in the center of where that pile of dirt was obtained from. But what I'd like to really draw your attention to is we know the altitude of the vehicle, we know the geometry of where the pipeline is, so therefore we can measure very accurately the altitude of the pipeline above the bottom. and where the shadow on the backside of the pipeline, where it leaves the bottom, as it's doing in this location, that's an area that has been scoured out. And those change all along the 4 miles or so of pipeline that exists under the Straits of Mackinac. So we can very precisely measure the unsupported pipeline spans as the bottom continually changes. And that's exactly what we began doing in 2015. We can create 3-dimensional images from the sonar image. This is a sunken barge here in the Portage Waterway, just adjacent to the university, left over from the copper mining industry, and it's 3-dimensional representation. We do that for the pipeline. We can tell regulators, Enbridge, what areas of the bottom are eroding, what areas are accreting across the straits, and what areas need to be watched in terms of increasing or decreasing span lengths of the pipeline. And then they respond by adding additional anchoring systems along the pipeline. The second thing we've done is add environmental monitoring to the Straits of Mackinac. These are one of our coastal monitoring buoys. This one has been deployed in 2015. It's owned and operated by Michigan Tech. This website presented here takes you to all the buoys that report to Michigan Tech. Each buoy reports every 10 minutes, 24 hours a day, but again, are only available during the navigation season. They will not survive a Michigan winter, and they will not survive the ice in the Straits of Mackinac. So we pull those out. So currently there is no observations of environmental data real time in the Straits of Mackinac once the buoy is pulled, but we're working on that as well, which I will share at the end of the conversation here. One of the important sensors on the buoy is a buoy-mounted acoustic Doppler current profiler. This ADCP monitors the current vector every 1 meter below the buoy all the way to the bottom. That is presented here in 2 slides to come. I forgot to mention here that the heavy lifting has been a partnership with the NOAA lab in Ann Arbor. They have set the mooring for us in the Straits and do the heavy lifting each year as one of their vessels is transiting the Straits. So the buoys are about 600 pounds in weight, and they are anchored on a loose mooring with a 2,000-pound sinker. These are the currents from the ADCP, and this requires a little bit of explanation. So as we move horizontally, we're looking at a week's worth of data. If you look very closely, these are actually current vectors. This would be 1 meter below the buoy and all the way down at the bottom, 28 meters below the buoy. The buoy is moored on the north side of the navigation channel in the Straits in about 100 feet of water. Blowing that up on the left side, you see that each of these really are current vectors. The magnitude of the current is related up here in the upper right-hand corner to the speed of the flow. So the bright orange colors are greater than 50 centimeters per second, or about greater than a knot. When the vectors are pointing below the line, as they are now, then that's flow to the southeast. That's flow out of Lake Michigan into Lake Huron. And similarly, when the vectors are above the line and pointing to the upper left, that is flow to the northwest, or flow out of Lake Huron into Lake Michigan. And if you go back to the whole assembled data on the right-hand side, you'll see that about every day and a half, that flow sloshes back and forth between flowing into Lake Huron or flowing into Lake Michigan. You'll also note that there are disturbances over here on the right side that begin at the surface and propagate downward. There's also disturbances that are on the bottom and over here on the left side that propagate upward. So it is extremely complex flow in the vertical. There is a late 1600s, I believe 1679 account by a French fur trader paddling his canoe across the Straits of Mackinac. Says it's the most complicated flows he's seen anywhere in the world, that it could be flowing into Lake Michigan horizontally on one side and flowing into Lake Huron on the other side. Well, we see that from the buoy data, we see that same complexity in the vertical as the French Voyager saw in the horizontal. And again, at the end here, I'd like to share that we are learning that fur trader was indeed correct. The third thing that brought our attention to the state was the development of the latest generation of predictive models for the Great Lakes. This was done in collaboration with the Ann Arbor NOAA Lab. They are running the same models on their computing system as we are here at Michigan Tech. But the flow is extremely complex and very dynamic through the Straits of Mackinac. I'm going to show you an example. I'm going to start the flow here, but then I'm going to stop it as quickly as possible and explain what you're looking at. So the red dots are released at the surface numerically into the flow. The yellow dots are released near the bottom. So you're going to see the difference between the flow in the surface waters in the straits versus that at the bottom. In the upper panel, the red curved line, this would be a late summer condition. That's the temperature profile, warm water on top, cold water in the bottom. And the vectors are the flow that you'll see reverses periodically vertically as we go from the surface to the bottom. So I'm going to start that. The other point I would like you to pay attention to is down here at the bottom. You will see the time go by very quickly. So the point is flows move very fast in the Straits of Mackinac, and they reverse very quickly, as we saw in the current meter data, and the model is capturing those dynamics. So we are now about 1 day into this simulation, and you can see how rapidly the surface currents are moving, and similarly bottom currents. And you can see that oscillation back and forth between the straits. You can see the magnitude of the velocity in the upper panel. So things happen very quickly, and that has very serious implications to being able to recover from a spill in the Straits of Mackinac. That brought us to the independent risk analysis, and the history of that is the Pipeline Safety Advisory Board. We developed 2 requests for proposals in May of 2016, one for an independent alternatives analysis, which is if you're going to transport the same amount of oil to market, how else might you do that? Or what other routes are available? And an independent risk analysis. Contracts were let to 2 companies. The alternative analysis was completed by Dynamic Risk in October of 2017. The risk analysis, however, failed due to a conflict of interest and was terminated by the State Attorney General in the summer of 2017. So essentially, the risk analysis was a year behind the alternatives analysis. The governor suggested to the Pipeline Safety Advisory Board that I resign my position representing Michigan universities and organize those universities to undertake the risk analysis. And that's indeed what happened. Pipeline Safety Board, with the absence of myself, voted unanimously to have that happen. The scope of work for the project was quite extensive. This is a schematic diagram of how we see that workflow. It begins with defining the worst case scenario, asking the question, where then does it go? Based on the extent of the spill, what are the timelines for cleaning that up? And then what is, in the second block, what is the risk to public health, to ecological health, and the cost of restoration. And then the final 3 sections deal with the damages and assessing the costs associated with all of those damage and economic losses. We felt, although that's extremely comprehensive, that there are issues that cut across all of these different areas. We've called those broader impacts. And it's in this area that we tried to address Native community concerns over the pipeline and other issues that cut across all of these different areas. We also implemented, and you'll see why in a few moments, a very extensive geographic information tool that characterizes each kilometer of shoreline in terms of its substrate, its type of material, its geologic and ecological function, and that is available and still operative as a tool for first responders and for the state. The team structure comes essentially from research ships, and that is my background, being a seagoing ocean engineer. There is a chief scientist on every cruise that is responsible for the quality of the science. So we have appointed a chief scientist for each of those 10 different areas described in that previous slide. We also appointed a section lead for each of those, which again is a subject matter expert in that particular area, but that was at Michigan Tech, so that person could interface very effectively with all the other teams on a weekly basis. And then there were 3 to 5, again, subject matter experts in each area assigned to actually do the work with the chief scientist and the section lead and to result in the final report. So a unique structure, but I think one that you'll see is critical to being able to manage the number of people involved. The way we proceeded is we asked the Vice President for Research at Michigan Tech to send requests to all of 13 of Michigan's public universities, to their Vice Presidents for Research, asking for participants. And that effort generated 8 individual responses. The final team ended up being 41 researchers, 20 of which were external to Michigan Tech. They were from 9 universities, 7 of which were Michigan universities: University of Michigan, Michigan State, Wayne State, Western Michigan, Grand Valley State University, Oakland University, and Michigan Tech. And 2 outside universities, North Dakota State University and Loyola University of Chicago. And that was because we had to do some headhunting to find experts in petroleum pipeline dynamics outside of our basin here in Michigan. There are also 3 consultants, part of the project, 2 independent contractors, which were former Department of Energy employees with great expertise in petroleum pipeline transport. And then again, a very close cooperation with the NOAA laboratory in Ann Arbor, providing their numerical modeling folks to work directly with our numerical modeling folks. And some good things came out of the advancements that we were able to make in the entire Great Lakes ability to forecast circulation in the Great Lakes. Multidisciplinary areas, you can read through those, but it's everything from human environmental health to, as I say, numerical hydrodynamics. So very broad group of people. And then an extensive GIS effort, which I'll describe shortly. We organized ourselves in a diagram that looks a lot like a clock, and that's because task A needed to occur before task B, which needed to occur before task C. So propagating that through the entire system and having a very short 6-month time frame to complete this analysis resulted in a structure where we needed to be constantly providing input to the latter tasks based on where the earlier tasks were in their development stage. And again, that was part of the reason for having a section lead that was in each section that was at Michigan Tech, where we could exchange that information. In addition, the broader impacts, task 10, you see kind of encompassing everything across the whole board of activities. So we, in summary, the members by university are presented here. And I think the most important thing to share is that no one university had all the expertise that was required. Michigan Tech came under contract to the state of Michigan as the lead on December 12th of 2018. All contracts were to the partner institutions by the 26th of January. Our contract with the state formally began on the 1st of February. We had by the 13th of February, we had 3 universities with signed contract. By the 21st of February, 5 universities, and by the 29th of March, all 8 universities and the other partners were all signed up. So it was essentially 2 months into the contract before all the universities were totally on board. This did not hamper the investigation. The researchers all had confidence in their business offices and began working on February 1st, right at the first day of the contract, with the hope and conviction that their people would come through, and that really was the case. So in terms of weeks after the contract, three were signed up in the 3rd week. We had 6 signed up by the 4th week, and the 7th and the 8th came on in the 8th and 9th week. And again, the smaller universities seem to be quicker and more agile, and the larger universities slower to get contracts in place. This is the graph that shows the distribution of people as a function of each of the tasks in the scope of work. And as you see, the people are distributed throughout the tasks in a very diverse way. For example, in terms of private and public costs, government costs, essentially they're distributed over most of the universities participating. So we sought out highly qualified experts in each of these various universities. And as I said before, no one university seemed to have enough breadth and depth to have completed this work. Some findings of interest. Task A, identifying and analyzing the duration and magnitude of the worst case spill. This was governed in part by the federal definition. CFR 194.5 defines a worst case discharge volume as the largest foreseeable discharge of oil, including a discharge from fire or explosion in adverse weather conditions, considering the maximum plausible potential release. So it needs to be the largest possible worst case spill. It needs to be foreseeable, and it needs to be plausible. And you will hear from Steve Keck, Sector Sioux, at the next webinar, and he has a great little proverb he told us in our meetings there about that. So I'll leave that for him to tell you next time. In going through this analysis and working closely with each of the groups, there is no way to define a single worst case scenario. The human health group obviously felt the worst case scenario is one that transports material to the most heavily populated area, which is to the east of the straits. Similarly, the ecology folks, the worst case scenario is one that affects the fisheries, breeding grounds, Waugoshans Point, and the areas to the west of the straits. So essentially going into this, we had 10 worst case scenarios, but then there is another big player here, and that is our ability to numerically forecast where things go. So looking at the bottom, there are essentially worst case scenarios that were defined by the computer simulations. That is things like the most shoreline oiled in each lake, the most surface area covered by floating oil, and the fastest spread of oil. So those are all scenarios that we derive from the numerical analysis. So it's a very complex process to define the worst case scenario. So what we did is drive as many of these scenarios through the entire cost analysis as possible and impact analysis. Worst case discharge, again, plausible and foreseeable. These could be pinhole leaks, and pinhole leaks, again, are defined in the federal regulations and come primarily from the high velocity rifle shot that went through the Alaska pipeline. So a pinhole leak is something on the order of 3 inches in diameter. Enbridge has automated systems for valve closers and a whole series of valves on both sides of the straits, as well as upstream across Highway 2 and downstream on Line 5. So it takes 3.5 minutes to automatically close those valves, and that can be done from a number of different locations, and these automated systems are monitored 24/7. But the operator has a 10-minute window in which to make a decision as to whether or not this is a real spill or not a spill. And this is a great improvement over the spill that they had in Kalamazoo. So if the operator exercises that 10 minutes of checking other data, then they have a total of, then the valves will shut down not in 3.5 minutes, but in 13.5 minutes. If the operator does not manually initiate the automated shutdown mode within 13.5 minutes, it will shut down on its own. So there's 2 time frames there, 3.5 minutes and 13.5 minutes. A 3-inch pinhole. Our first level of failure is shutting down pipeline in 3.5 minutes, which results in 4,400 barrels, or shutting it down within 13.5 minutes, which results in 8,600 barrels of oil. Same thing could happen in both pipelines, and the numbers associated with the 3.5 minute shutdown and a 13.5 minute shutdown are presented in Tier 3. Similarly, Tier 4 is a full rupture of one pipeline, and Tier 5, a full rupture of both pipelines. Enbridge supplied in writing to the state prior to this analysis starting that it took 2 hours to manually shut down the valves. They then refined that to 1 hour, but again, the analysis based on the worst case, foreseeable, plausible catastrophe. So again, we used the 2-hour worst case scenario for a single pipeline rupture of 29,000 barrels, or for both pipeline ruptures of 58,000 barrels. And then that's what carried through the entire analysis. Fate and Transport is predicting where that 58,000 barrels of oil could go. Model has used weather conditions such as wind speed, currents, actual water and air temperatures, ice cover, and then advanced the modeling to include oil weathering and evaporation, to simulate how it would actually move and what quantities would be at each location. We ran these models for an entire year. The year of choice was 2016 because weather conditions all around Lake Michigan and all around the Lake Huron were available at 6-hour intervals for 2016. So we used the actual weather that occurred on both lakes for that entire 365-day period. Simulations show oil dispersal on the water and in the air, and when and where it would reach shoreline. We did an analysis of 4,380 simulations. That is a simulation every 6 hours for 365 days of 2016 at 3 locations across the straits, a northern location, a central location, and a southern location of the pipeline, again, chosen to be the worst possible places to have a break or a pinhole. And that each of those 3 locations, every 6 hours, we released 10,000 particles from the north one, 10,000 from the central one, and 10,000 particles from the southern one, and then tracked their locations of all 30,000 of those particles for a total of 60 days to make sure that we accounted for all their possible locations and where they ended up, where they went to shore. And I'll show you some of those simulations. So, in a very extensive numerical modeling effort. Some sample results. The maximum shoreline oiled in one spill is 2,006 kilometers spread across 514 of the model's 1 kilometer square grids. cells, mainly in Lake Huron. The largest area of open water covered was 1,745 square kilometers. Lake Huron shoreline was oiled in more scenarios than Lake Michigan, which shows the persistence of our primarily westerly flow of winds in this area, driving flows from the straits into Lake Huron. And many scenarios showed oil reaching both lakes as the two lakes oscillate back and forth connected at the straits. Movement of oil depends on the weather in the hours and days immediately after the spill. Oil could move into one or both lakes. The maximum shoreline impacted was 1,021 kilometers in Lake Michigan, 2,006 kilometers in Lake Huron. Volatile organic carbons would most likely dissipate over the water, limiting effects on population centers. We then moved, once knowing where it is, where it goes, how long it takes to clean up, we then moved into estimating the economic damages using environmental economists from all across the basin. Recreation and tourism losses consist of loss of value of recreation users and loss of income for tourism and recreation related businesses. Other private costs and losses result in impacts on water supplies, impacts on energy supplies, impacts on property values, commercial shipping, and fishing. The total of all those damages are almost $1.4 billion. You add them up. In addition to that, there are governmental costs of a worst case release, and they correspond to responding to the spill emergency, conducting damage assessments, monitoring cleanup activities, overseeing restoration efforts, negotiating a settlement with responsible parties, and lost tax revenues. And again, those come out to somewhere between 461 to 873 million. There are partial gains due to income tax paid by the cleanup workers of 131 million, leaving a net government cost of somewhere between $300 and $750 million added to the 1.4 billion before. And then there are intangible losses. There is very strong opposition from Michigan's 12 federally recognized tribal nations. Their legal rights, economic dependence, cultural and religious identity are highly valued. Traditionally used flora and fauna for subsistence and cultural purposes, burial, and other sacred sites. And there is a strong bias for litigation and potentially against the state is nearly certain. Lakes would be impacted. Up to 40% of the oil could be recovered from the water surface. Shoreline cleanup would take 12 to 24 months. Sensitive and threatened habitats and species would be harmed. For the spring scenario, expected to result in the highest total damages of liability is estimated at 1.3 billion in economic losses and 500 million in restoration costs. In addition to the total liability, approximately another 200 million in net tax revenues would be lost. Intangible costs would also be very high. So, not to end on that extremely negative note, there is some good that has come of this. We have greatly advanced the state and numerical modeling in the Great Lakes, again, with a very strong collaboration with NOAA GLERL. We have just recently tested high-frequency radar for mapping the currents in the Straits of Mackinac, and I'll share some of that with you very shortly. And then we continue our work in autonomous underwater and surface vehicles for environmental monitoring and cleanup. So this is one of these worst-case scenarios from the new advanced model. The particles in turn that we release, the 10,000 particles in this simulation, and this is the worst case scenario for maximum impact. You'll notice that it happens 2 days after Christmas, December 27th in 2016. The green particles are those that are beached in the relative percentages. So again, things moved very, very quickly. We are now 24 hours into the simulation. As you can see right now, there are 40% of the particles still afloat. 85% are now have reached the beaches. We keep track of the latitude and longitude of each one of these particles, both as it travels across the water, as well as where it lands on the beach. And that's the basis for the environmental and all the other cost assessments. Here we are now, 175 hours into the simulation. There's only 2.3% of the particles left still afloat, and the particles that are beached are about almost 98% at this point. So things happen extremely fast, as the models are showing us and our experience shows us. And again, the logistics associated with tracking this floating oil and trying to clean it up on water is not to be minimized. Real quickly here, to save plenty of time for questions and interaction, we just recently, May 20th through 25th, completed a demonstration of high-frequency radar in the Straits of Mackinac. This has been funded by the Great Lakes Observing System, part of the Integrated Ocean Observing System. The Great Lakes are the only coastline in the U.S. that does not have operational HF radar. Theory being that HF radar does not work as well over freshwater as it does over saltwater due to the electromagnetic connection between the radio waves and the water surface waves. But by not working so well, it works out to about 20 kilometers offshore in the Great Lakes, where it works to 200 kilometers offshore in the ocean coast. But for us, particularly in the Straits of Mackinac, being able to map the surface currents of 20 kilometers in either direction is a big success. So we have been fighting for a number of years to get this opportunity. HF radar is a bit of a bad name. It is not operating in the radar frequency band of the electromagnetic spectrum. It's operating in the FM radio band at 41 megahertz roughly, and very low power systems. This is a 40-watt system, one station on each side of the straits. We have bore-sighted each of these antennas so that they're pointing to the area of most interest, which is directly over the Enbridge pipeline. And what it does is where these two radar beams, station one being located at the fort here, station two being located at Bridgeview Park, again, both on DNR land. Where those two beams intersect, one can determine the surface current velocity vector. And again, recall the discussion with the French fur trader about how crazy the circulation can be paddling across the straits. We see a very strong coastal jet on the south side, and again, responsible for moving those particles very quickly to the east. We see weaker flows in the center and a little bit of a jet on the northern side. These 4 frames I'm going to show you are 1 hour apart, and we happen to catch one of those reversals. This is an hour later. This is an hour later than that. You can see some of the flow is beginning to reverse, but it's doing so in a big gyre, or counterclockwise turning gyre, and then an hour later, everybody's going the other way. So again, very complex flows in the horizontal, just like we saw in the vertical, but I think you might agree that if you're trying to organize an oil spill cleanup, very valuable to have. If this system were to go operational, we would have a vector current map like this produced automatically, instantly available on the Buoy website every 1/2 hour, 24/7 throughout the winter. We're also working very closely on the development of further autonomous marine vehicles. This, for example, is a Coworker 5 made by a company called L3 ASV Global. We believe it to be one of the very best available world leaders in autonomous vessels. These vessels can operate for 7 days at 24 hours a day at a speed of 7 knots, bottom mapping, pulling oil boom, whatever. Diesel powered, can be operated either under supervised economy or fully autonomously. We just demonstrated this vessel for the governors, Great Lakes governors and premiers in Milwaukee a couple of weeks ago. Brought this vessel up from Louisiana. On AIS, you can see it is designated as an unmanned vehicle. This is an interesting picture. This is in the inner harbor of Milwaukee. You can see the ASV Coworker 5 working here on an autonomous pattern, being supervised from inside the Discovery World facility. Sailboat came over to take a look at it. The cruise boat came over to take a look at it. So again, they have collision avoidance. They know the rules of the road. They're really quite advanced and I think hold a lot of promise. Our goal is to try and obtain at least one of these to be shared amongst Great Lakes universities and other entities. This is a picture of Michigan's governor concentrating hard on manually driving the vessel. And thank you again for your attention. Glad to answer questions as they come up. Thanks.
This is Mark Breederland again. Guy, thanks so much. That was an excellent talk on big team science, fascinating dynamics there. And I want to introduce Geneva Langland at our Ann Arbor office, who's going to help facilitate some questions and answers that people have been typing in the box on the right side of the screen. Geneva?
Great. Thank you, Mark and Guy. Hopefully everybody can hear me now. This is Geneva Langland. As Mark said, I'm coming in from Michigan Sea Grant's Ann Arbor office. And the question and answer box is ready and open for anyone who has comments or feedback or anything that they'd like to ask. We have one question. Which oil spill trajectory model did you use? Guy?
We used what is called FVCOM, and that stands for Finite Volume Coastal Ocean Model, developed jointly between us and the NOAA Lab. So it is a new framework of doing hydrodynamic modeling. It is considered the best available. And then in addition to the base model, we added the added complications of ice and did that in a robust way. Its ice presence not only does not allow the wind to couple with the water surface to drive the currents, but it also modifies the flow because of its presence in the upper part of the water. And both of those effects are now included. We added to that the actual temperatures throughout that entire year of 2016 that the oil would be transmitted into, and that affects the rate of evaporation of those oils. So that has been included into the modeling now too. So the model is quite robust. And again, we did comparisons with the buoy data for 2016 and the modeling results track one for one with the buoy observations. So we have a high level of confidence that we have a very robust model. That model is becoming operational by NOAA GLERL for the Straits very shortly.
We have another question about the challenges of building models and conducting risk assessments when there are unexpected events like big severe storms or media tsunamis. How do we incorporate those into risk assessments and models, given that they are rare events and hard to monitor?
Yes, and that was the primary reason for using actual weather that occurred for an entire year of 2016. And so those events as they occurred in 2016 were incorporated into the model. And again, when we asked the computer what was the conditions that led to the fastest dispersal of oil, those events played into that assessment. Similarly, the oil that was transported the greatest distance or followed the greatest length of shoreline are the results of those big storms. The one I showed you the example for with the green and red dots that happened on the 27th of December was one of those such events. It was a big storm that happened 2 days essentially after Christmas. There was some ice present, but ice was forming. There were sufficient conditions in the early part of the storm so that no cleanup operations were possible. So all of that information, all that real occurrence was in the analysis that we did.
Thank you. Given that high lake levels are such a topic of concern across the Great Lakes Basin right now, we have a question: do lake levels have an influence on oil movement in the models?
They do in a couple of ways. The shallowness of sensitive areas like marshlands, their nearshore slopes are about 1,000 to 1. So we add a foot of water level in the Great Lakes. We add, then that intersection of land and water can move as much as 1,000 feet. So it plays a big role in terms of where water and land intersect. The other thing that we know happens with rising water levels is the storms that bring the precipitation that ultimately ends up in our high water levels in the Great Lakes also bring very strong winds. So we're seeing during these high water periods more frequent and more intense storms across the Great Lakes. And again, 2016 was about in the middle of this rise of lake levels, but we continue to see more frequent storms and stronger storms, larger waves. And again, all that is critical to the ability to clean up. You may know that Governor Snyder entered into an agreement with Enbridge that they stop pumping oil through the pipeline anytime the waves are greater than 8 feet. That was not based on stress on the pipeline. It was based on the inability to clean up oil spills when there are large waves present. So there is a recognition that these severe events are having an impact on the ability to clean up an event of such as this.
Thank you. Were any scenarios run on these releases that used less than the 58,000 gallon worst case scenario?
They were all at 58,000.
Were there any that used less than that? I think that was the question.
Oh, I'm sorry. No, they were all at the maximum worst case.
Okay, thank you.
But maybe if I could add one more thing to that.
Certainly.
The quantity of oil does not predict where it will go. So a lesser spill will still oil the same places and the same amount of shoreline. The oil will be just less thick along those sections of shoreline. So where it goes is controlled totally by the weather, the currents, and the waves, and not by the quantity of the oil, which is probably what the asker of that question was really trying to get at. So my apologies for being slow on the update there.
Nope, you're fine. Thank you. We have just a few more minutes left for questions. So if you have other burning thoughts you'd like to express, please make sure they get into the question and answer box soon. We have a question about that public and private costs associated with the damages of an oil spill. Did the analysis take into consideration the potential impacts on tourism, both the impacts that are physically tangible in areas that are affected by the spill, as well as the negative perception that people might have in the Great Lakes because of a spill event?
Yes, it did. It took both of those into account.
We've got a question here. What can you say about the risk assessment in terms of how it did or did not address the probabilities of a pipeline failure as a consequence of current shifts on the bottom of the straits from events that may not have been incorporated into the original design of the pipeline?
The presumption for the scope of work that was dictated by the state was we assume that the worst case scenario has just happened and what is the total impact economically on all the states and surrounding area. So the initial assumption was the worst case scenario just happened and we go from there. There was no analysis done by us or anyone else, to my knowledge, at this point, other than the private citizen groups that have done such analysis. as to what the probability that certain conditions would cause those types of failures. Up to recently, most people felt that a severing of both pipelines was a near implausible possibility. And then surely a year later, we have a large commercial vessel dragging an anchor through the straits and denting both pipelines. So, what we think is sometimes not conceivable really is conceivable.
Very true. We've got a question about drinking water intakes. Did the oil movement in your simulation affect any public drinking water intakes in the modeled scenario?
Yes, it did. And again, those costs were estimated by the economics team. The other factor that was somewhat surprising to us is that several of the islands, there are not commercial intakes, but individual private intakes where people acquire their drinking water directly out of the lakes. And again, we went to the individual property owners and estimated the number of wells where that happens, or water intakes where that happens. And again, some accounting was made of those impacts as well. So it is not just commercial municipal intakes, but it's also private intakes.
Great, thank you. Just another minute if anybody wants to shoot another question into the box. In the meantime, here's a more open-ended one for you, Guy. What do you see as some of the big conversations that we'll be having about crude oil transport in the next 5 to 10 years that may be just starting now? What are some of those coming conversations?
I think everyone is committed to making the straits and other areas as straight as possible, as safe as possible. And I think the big impacts will be how do we make them safer, and at the same time, how do we provide the petroleum that unfortunately we're very much hooked on at this point and will be for the foreseeable future. The alternatives analysis shows that, and other experiences also show that pipelines are far safer than transporting petroleum in barges or on railroad cars or down the highway. So I think the big efforts will be how do we make pipelines safer in the near term, and that's what I encourage people to concentrate on.
Well, this is Mark Breederland, and it just turned 3 o'clock Eastern time. So I just want to thank again Dr. Meadows for an awesome talk, very fascinating. I want to thank all the people who have joined us and participated in our first webinar of 2019 hosted by the Great Lakes Sea Grant Crude Oil Transport Network. Again, the recording is going to be on the website. And thank you so much to our team Ann Arbor that just did an awesome job and kind of doing all the behind the scenes work on doing this webinar. So thanks to everybody for joining in. Have a great day, and we'll look forward to the next one, July 23rd, same time with Stephen Keck from the U.S. Coast Guard. Thanks again.